All right, today's lesson is on integration by using partial fractions, or decomposing a complicated integrand or a complicated rational function into smaller, simpler fractions that have numerators that are constants. So that's where we're going. So let me just read this. You should have this down in your notes. A rational function integrand that cannot be easily integrated by use substitution or by parts, that's, remember the DI method, integration by parts that we just talked about, can sometimes be integrated easily by decomposing the rational into fractional parts with constant number numerators. The predictable process of decomposition is the basis of this lesson. And so if you think about it, what is the integral of 1 over x? Do you remember what that is? Ln of x, or ln of the absolute value of x, okay? So if we have a rational function that's really, really complicated, then you can't just take the ln of it, right? But if it's a 1, or if it's a 4, or if it's a 17 over some kind of function, then you can use, then you can integrate that into a logarithmic. So that's what we're going to do. Now, just to explain this, okay, I want to show you how we simplify these two rationals. Okay, so let's add these two rationals. What do we have to do? What's the big deal? What's the important thing to remember when we want to add fractions? What do we have to get? A common denominator, right? So I need to multiply this top and bottom by x plus 3. And over here, I need to multiply top and bottom by x plus 2. Okay, so we're all in agreement there, and that actually is very, very correct. So we have x plus 3 plus 5x plus 10 up top, all over x plus 2 times x plus 3 on the bottom. Now, when we simplify the top here, what do we get? We get 6x plus 13. So I'm just going to do that here right now to save some space. You can rewrite that, of course. 6x plus 13. Now, this is the simplification of the sum of these two rationals. Okay? Now this, obviously, just take a careful look here. We started with constant terms without any x's in them. When we simplified, now we have a binomial that has an x in it. Okay? So this would represent sort of a complicated, I'll put that in air quotes, integrand. These right here, the original fractions, would represent very simple fractions, right? And so anyway, so this is what we're going to be doing. We're going to be breaking up rationals that look like this into partial fractions where the numerators have numerators are constants. Okay, that's what we're going to be doing. And so in essence, the next point here, decomposing a rational fraction is the reverse process of what we just did. And sort of the overall, the general, sort of formula for this would be that if you had some function up top, and this is sort of type 1 actually, just like the question we just did, but if you had two separate binomial factors, you would always be able to split this up, no matter what f of x is, always be able to split this up into two partial fractions where one of the factors is, makes up the first fraction, and the other factor is the denominator of the second fraction. So this will always hold true, and we're going to do some examples where this, and this is sort of type 1. There's probably at least two different types I'm going to show you for this course. Okay, one where the factors are different, and for sure I'll show you some examples where the factors are the same. There's multiple of the same factors. Okay, that's a different. You have to do that a little bit different. But this is version 1. Now this only works, okay, where the degree of the numerator, so that is the largest, exponent that we have on any of the x variables, in the numerator is less than the degree in the denominator. So notice here, the degree here for this numerator is 1, because it's a simple, linear, right? And this one is going to be a squared, right? X squared. So it's going to be degree 2. So this works if it's like this, if the degree is at least 1 less. If it's equal, not going to work. If it's greater in the numerator, not going to work. It should be noted, though, that if we have the case where the degree of the numerator is not less than the degree of the denominator, we can perform polynomial long division or synthetic division, we can divide and actually split that up and then go from there. But that would be an extra step. So let's just focus on this. Okay? So I'm gonna just mention a couple other things. Okay? The reason why we're going to do this, and as I sort of mentioned already, the integral of something like this may be very daunting. But the integral of this, being that a is a constant, and this, being that b is a constant, becomes very easy. And we spoke earlier about the integral of, let's say, 1 over x, right? If you integrate that, that's very easy. You get ln of absolute value of x, right? And so consider this. If we just have a constant up here, then these are going to be pretty easy to integrate, generally. And so that's our hope. By splitting these into partial fractions, we'll be able to integrate fairly easily with just constants there. Okay? So this side is much easier to do in many cases than this side. This is the process. So we're going to be using such things as substitution to solve for a and b, equation addition and elimination, and also just sort of basic equation logic, which the first example, you'll see it's, I don't know, it's just kind of using logic to determine what these coefficients are, but there are a number of different methods. Okay, so what we're going to do is I'm going to show you how to decompose into partial fractions that first example. Okay, we're going to work backwards from that first example. So what was it? 6x plus 13 on top. And you know what? Well, let's go ahead and do this. Let's say it's x squared plus 5x plus 6. Okay, so we're going to decompose this. All right. So what we want to do is we want to see if we can factor. And the top doesn't matter, but we want to see if we can factor the bottom. Because, again, we know that the degree is, you know, the relationship between the degrees is good, so we can do this. It's less on top than on the bottom. But if we can factor this, and we know already this is factorable, right? So 6x plus 13, can leave that one alone. But down here, this can be x plus 2 times x plus 3. And that's really important. We need to work with factors here in order to do this type of decomposition. All right. So we set things up just like we kind of left off. And I guess I'll just use that same color. So 6x plus 13 over x plus 2 times x plus 3 is going to equal some partial fraction that is a constant over the first factor, which we'll make 2, x plus 2. And we're going to add to that another partial fraction with a constant in the numerator and the second factor in the denominator. So now we need to solve for a and b. Okay? So let's just see. What we're going to do here is we're going to multiply everything, every term on both sides, by x plus 2 times x plus 3. That's something we can do. Again, we're simply solving, but we have two unknowns here, not just one. So we're going to start off by doing this. That's going to give us, 6x plus 13 equals a times x plus 3 plus b times x plus 2. So hopefully you'll see how some of these factors will divide out, right? And this will get rid of all the denominators, right? So there's no denominator left. That's what we want. All right, two unknowns instead of one. So this is a bit tricky. However, one of the ways we can do this is by expanding. And I want to, and let's try and gather some like terms whatever we can. So I'm going to rewrite this. We're going to go ax plus 3a plus bx plus 2b. Now, if we align these terms to common terms, and again, we have two unknowns, so this makes it just a little bit different than we're used to. But watch what happens when I bring ax and bx together, because those would be common terms. Let's just write them side by side. And I'm going to put 3a and 2b side by side as well. Now, factoring, and what can I factor out of this first grouping here? I can factor what? X. So if I write this, and I'm going to write it like this, okay? So don't shoot me, but just be patient. I'm going to do this a plus b times x, okay? You good with that? Plus, and of course this is just, I'm going to group this together, common factor, nothing but 1. All right? So I'm just going to group it like that. Now, watch this. This is super cool, and you may see this already. But honestly, I think this is kind of cool, and a lot of students don't see this right away. And it's kind of like, oh, yeah, that is so super cool. How come we didn't learn how to look at it this way before? But we never had to with only one, unknown. But now with 2, okay? Can anyone see some relationships here? What, did I write something wrong? Oh, okay, what are you saying? What are you suggesting? Sorry? A plus B?
A plus B equals 6 and A plus 2.
You got it, Jin. Nice. So check this out. Watch this. I think this is super cool. Look at this. We have an x term and we have a constant term, and I'll just kind of underline them differently. Over here, we have an x term and a constant term because a and b are both constants. We have, here's the x term, and here's a full constant term. So, very good. Good to notice that. We now have 6 equals a plus b. Right? And we also have 13 equals 3a plus 2b. All right? Now, from here on, we have some options, I guess, right? I mean, we got to do some substitution or something like that, right? So we could say that a here equals 6 minus b, I suppose. And then over here, I could substitute that. So here's the substitution part. 3 times 6 minus b over here. And now I get just one variable to solve for, which is awesome. 18 minus 3b when you distribute that. Subtract the 18, we get negative 5. Negative 3 plus 2 is negative b. So b equals 5. And then, of course, a equals 1. Now, notice that a and b, a is 1, b is 5. A is 1, b is 5. Is that true? Because we started off with this example, and what did we have at the beginning? Oh my goodness. 1 and 5. See that? Okay. So now, the tricky thing is there's 2 unknowns instead of just 1, so you got to use logic, substitution, this sort of thing. Okay? So on a scale of 1 to 10, how difficult was that example? Or was that pretty good? All I heard was moaning and groaning back there. Is that a negative value then? Not even 1 out of 10? Okay. Long, but not that hard. Oh, long? You want long? Long is coming, okay? That's the shortest example I have. All right?
Yeah, it was boring.
Yeah, okay? Yeah, long is coming. Boy, I should be quiet with those guys back there. Sorry, keep working. Got a split class going on here, if you can imagine that. All right. Now, are you ready for type 2 then? Let's do an example from type 2. All right. This is so much fun. So this is teacher fun, not student fun. It's teacher fun. So this would be type 2. I'll just type this. Nope. I'll write this. I'm not typing it. Type 2. Now this is, we're going to call this repeated linear factors. Okay? And so here's the example like this. Let's say we want to decompose this. Now that looks pretty much the same as the other one, right? Except we do have to do things just a little bit differently. And to tell you the truth, right now I can't explain to you why this is so different. I really can't. Other than this is the pattern that we have to work with. Now it does look like we have x plus 3 times x plus 3, which is totally true. But because these are repeated factors, the fractions themselves cannot be set up exactly the same way as the type 1, as the first one. Okay? And it's just kind of the way it works, I mean, through pattern, and like I say, I can't give you much of an explanation as to why that is right now. Maybe later I can, okay? But right now, we have to set up a little differently. And so what we have to do is this. Still a here. What we're going to do is we're going to take one of these repeated factors as the denominator, okay, for right here. We're going to add to that another fraction with b, but instead of just doing the other one, what we have to do is now both repeated factors. Just the way this is going to work out, okay? And I might do a little follow-up video here once I have a really good explanation for why this is true. But for right now, we're just going to go with this pattern. So when it's repeated like this, you always have to do this. Take one of the factors for one fraction. Then take two of the factors that are repeated for the second. If there was 3 or 4 or 5, you would have to do this that many times. One factor, and then the factor squared, and then the factor cubed, then the factor to the 4th. You would have to do that many times. Okay? And I guess the third type was where there's repeated factors and a separate one. And then you just, oh yeah. I tell you, that's the shortest example I had, the first one. If you kept going up in degree, then we would have, if this was 5, I would have to do x plus 3 cubed, and then another one, x plus 3 to the 4, and another one, yeah, it would be c, then d, then e.
Even though they're then f?
No, they're asking about a different question. So let's now continue on with this one, okay? Let's just take one thing at a time here. All right, anyways, you guys. Okay, so what's the first thing we're going to do? What are we going to do here?
Multiply.
Thank you. Multiply by what?
X plus 3 squared.
X plus 3 all squared. Thank you. So that will give us x plus 5 over here. That will give us a times x plus 3 plus b times
B.
just b,
How?
because these are totally gone. Okay? All right. Now, this one's not actually that complicated at all. However, we do need to do a little bit of expansion here. So this is ax plus 3a plus b. Does anyone recognize anything that's remotely similar to the last one?
Ax is equals to x.
Ax equals x, or more importantly, a equals
1.
a equals 1. And 3a plus b equals 5. Since a is 1, we know that b is what? B is 2.
Wow.
So that wasn't that hard either. Actually, you know what? Technically, this might be a little bit of a shorter example than the first one, right? Technically, sorry. Maybe it is shorter. I'm sorry to disappoint you. Thought this was going to be longer. So what we can say then, now, what we can say, and you can rewrite this if you want. I'm just going to cheat here. I'm going to copy this. So what we can say here is, oh, come on, Nelly. What we can say here now is that A is 1, B is 2, and here we go. I've got this totally decomposed. 1 and 2. All right? So here's the thing. See? Well, it's right here. 1 over x plus 3 plus 2 over. Now, if you expanded this out, it should work out that this is exactly the same. But consider this. This is why we're doing all this. This right here. Where do you go from this? Substitution? X plus 3. Do you have the derivative? Nope. What are we going to integrate by parts? Possibly. Yeah, we could, probably. But what if we just did these couple simple steps here to just split this up? Then this plus this is actually not too bad, is it? Okay. Okay? So that's just another way to do that. And again, I won't kind of get into this just yet. I will eventually. But we want to practice doing decomposing. Okay? So, all right. You guys with me?
Yes.
All right. Now, let's do the monster of all questions here. Example number 3. This is type 3.
Okay, I have half a page left.
You have half a page. You need more. Okay?
Are you serious?
Yeah, I barely squeezed this whole thing onto one page. This example. Okay? You ready? Okay, so I'm not actually going to just write out the whole question for you. I'm going to stop here and make sure we understand what's going on here. So we're going to use partial fractions, okay, but we have to split this up to, I don't know why I just made that noise. I don't know what that was. There's your first partial fraction.
Why did we get to
Oh, just be patient. Now what's this? This next one is going to be what? To the power of?
square?
2. So we got to keep going. C. This is x minus 1 to the power of?
Third.
3. Now, yeah, we have to do the other one. Absolutely. So this is D. X plus 1. Okay, so there we go. Those are our partial fractions. Now, if we stopped shy of that, we would not be able to get, all these constants in the numerator. So we have to expand it out entirely there. Thank you. Okay, so process is the same, but now we have 4 constants as opposed to just 2, right? So, or 3. So it's going to be just a little bit of a longer process, but it's not going to be too bad. All right, so let's multiply. So we end up having 2x squared minus 3 over here. Okay, I'm going to have a times x minus 1 squared times x plus 1. And I'm going to have b times x minus 1 times x plus 1. Now I'm going to run out of room, so what I'm going to do. Oops. X minus 1 all cubed.
Because
Okay. Okay, so just while you're doing that, just to go back, I'm multiplying every single thing by the denominator of the one on the left side there. So some of these are canceling out. One of these are canceling out with one of those. That's why I have a squared. And then x plus 1. So on. Okay? All right, so what we can do now, wait. I'm glad you said that. I heard that. This is going to be so much expansion. Now, here's the thing. We're going to be able to save some work. We're not going to have to expand all this. So this is slightly different than the first 2 examples in that we can now use some straight substitution to help us whittle down. And when I say whittle down, I mean like eliminate some of these whole terms. For example, okay, if you let x equal 1 and substituted that into the equation, do you see what would happen if you let x equals 1? Now, if we let x equal 1 to every term on both sides of the equation, we're not actually interrupting anything or changing, manipulating anything. But what we're doing, if x equals 1, so let's just write that down, let x equal 1. What happens if I let x equal 1?
C, we can find C.
So on this side, we're going to have this. What happens to this term if x equals 1? Here.
0.
Look at this. 1 minus 1 is going to be one of the factors here. So that's going to be 0. Plus, what if x is 1 here? Oh, boy, this is 0. 0. Look at, we've gotten rid of 2 constants right away. Now, we're going to have to deal with them later. But we are going to now have this. C times 1 plus 1 is 2. Plus D times, what happens here? Look at that. That's gone too. Wow. Okay. So the only constant that's left here in this new equation now by doing one simple substitution is C. So what's this? This is 2 minus 3, that's negative 1, equals 2C. So C equals negative 1/2. Does everyone see that?
Wait, C is negative 1/2 at 1 or always?
Okay, that's a good question. Is C negative 1/2 just at 1 or always? Well, remember this whole partial fraction thing. This is true all the time. So it's an equation, and as a matter of fact, I should bring this up now. You may see in some textbooks, you may see an equal sign with a third line here. And I know you've probably never seen this before. You may see this, and actually in one of the documents that I've studied here, that they use this for back up here, okay? Way back up here when I did, where did I go? I guess I messed it up, but this right here, they actually use a third line here, which means that it's exactly identical for all values of x. So not just over an interval, not just for a certain domain, but everywhere. So that's a very good question that you just asked. And this C is going to be negative 1/2 for all of it. Okay, so we've got C in the bag now.
How does that make sense? Like, how do you just pick a number?
Well, if you have a lot of different constants, right, and you just pick a value. Okay, so on this function on the left, right, remember these two are exactly equal. So if I can identify one of the constants, like part of it, by just substituting a value in, so say x equals 1, so at that point, you know, this is what the function equals. So if I can get part of the truth of that function, you know, that's fine. Now, if I pick another x, because we're going to pick another x now, which one are we going to pick next?
-1.
Thank you. We're going to pick -1. And so -1 is going to give us a hint how to algebraically solve for at least one of the other constants. And then we'll just start piecing them off. These are very good questions. I struggled with this as well. So I'm glad you brought this up. But let's give it a go. So I'm going to erase this work here right now. And this.
So if you have a question like this, you should try to look for what gets you to 0?
You should try to look for what gets you to 0 for one or more of the terms. Exactly right. Okay, so x equals -1. What am I going to be left with here? And I will write, so 2 times -1 squared minus 3. Okay. Oh, I should do that in black. So what's the left side going to equal? It's still going to equal what? 1? -1? Okay, still going to equal -1. So -1 is going to make, it's going to make this a term 0, isn't it? So the a term is still going to be 0. -1 here is going to make the b term 0. -1 is going to make the c term 0. Doesn't matter what c is, because if x is -1, doesn't matter if c is -1/2. That whole term is going to be 0. So this is good. And then this is going to be what? What's -2 all cubed? It's going to be -8 times d. Everyone see that?
Yes.
So this is great. Now I only have, by simple substitution, I only have one unknown here. This is going to be -1 equals -8d. d equals +1/8.
Is it -1 minus 1?
Yeah, -1 minus 1 is -2. So -2 cubed is going to be -8. All right. So we've got C and D. Got C and D. That is really good. Okay, so now we got to look for A and B. So I'm just going to erase some of the stuff again here. Okay. Now we need to find A and B. So of course I can use C and D, can't I? I can use C and D, but here I believe that this is now where we're going to have to do some expansion. Okay, so we're going to have to expand this, but we can use our constants for C and D and see where that gets us. So let's take a few moments to expand this A kind of term and the B term. Okay, so just go ahead and do that, and then we'll see what we come up with. Okay, so as we resume here, I hope you had a chance to do this expansion. Now this is my expansion, maybe a couple steps in. Okay, but this is sort of what we have. Now, we have A and B left. I included C and D into these terms here. Okay, I include C and D there. Now, what we want to do is, remember that logic that we used in the couple examples ago, where, you know what, was there a squared term, so let's compare the coefficients, or a constant term, compare the coefficients. Now, watch this. A is going to be part of a cubic term here when you expand this in, right? So if you use your head, you don't have to expand everything, and like you stop right here and you say, hey, listen, there's only one cubic term that has the A value, right? Is there another cubic term anywhere else? Oh, there's one over here. So you know what you do? You say, what's the cubic term on the left side? What's the cubic term? What's the coefficient of the cubic term on the left side over there?
Wait,
What is it?
isn't that a square?
Yeah, that is a squared. What's the coefficient on the cubic term? Luke? No. Pay attention. On the left side.
0.
Thank you. There is no cubic term on the left side. So guess what? There's no cubic term. 0 x cubed. Now, watch this. Watch this. Where are the x cubes over here? You do not have to expand this all out. I see ax cubed right here. Let's see. No. Plus 1/8 x cubed over here. So look at, I only have one unknown to solve for, and that's the A. And I'm still running out of room. I can't keep everything on the right track here. But I'm going to have to erase some things here. Okay, I'm going to have to erase this. Sorry, that's gone now. Okay, you guys solve. What is A? Yeah, what is A? Go ahead and figure out what A is here.
Number is a negative 1A. My number is a negative
Don't
1A.
psych yourself out. Don't psych yourself out.
Okay.
Whoops. What the what? What's going on here? I'm trying to just move this. Can I move it? Sort of. Okay, so what is A?
Negative 1/8.
Okay, so that's gone. Negative 1/8 x cubed equals ax cubed. That means A equals negative 1/8. Very good. Okay, there you go. That seemed too easy, didn't it? But if you use that little bit of logic there. Now, can we do the same thing for this squared term, which B is involved in a squared term here? Can we do that? So let's do 2x squared equals, where are the x squared terms over here? Oh, I have negative ax squared. Do you see it?
Yes.
Negative ax squared. Oh, just would you quit complaining now? We have to do all the squared. We have to do all the squared. Okay, come on. Hey, I'm recording this. This is supposed to be a real lesson here. Negative 1/8 times what? I don't have time to edit these videos, you guys. Look at, I'm doing all the work for you here, okay? Pay attention. Minus 3/8 x squared. Okay. Now, I got two unknowns here, or do I?
Or do you?
No.
Dun, dun, dun. I know what 8 is, guys. We know what 8 is. We just solved for 8. So guess
Oh
what?
my goodness.
8. We solved for A. That's what I meant. So A is negative A is actually positive 1/8. Okay. So we can gather some like terms. We can solve for B. I'm going to have 2x squared over here. I'm going to have negative 1/8 x squared. I'm going to have positive 3/8 x squared. And that's going to equal bx squared. So what is all this when it's all said and done over here? If this is over 8, that's 16 over 8. Minus 1 is 15. Plus 3 is 18 over 8. 18 over 8 x squared equals bx squared. B is?
18 over 8.
Well, 18 over 8.
9 over 4.
Thank you. 9 over 4. Okay.
All right.
9 over 4. Okay, so we are very close to being done now. So let's see. I've got A here. This is so exciting. The culmination of all of our efforts. And I'm going to erase most of them. Okay. Yes, this is going to be all gone. Okay. So watch this now. Now, the final nail in the coffin here.
We know what's the end.
Yeah, we're done solving. But now we have to do is we have to rewrite sort of what the answer is there.
What?
Wow.
Yeah, now, yes, the next step is you're going to have to integrate all of these. But that's not as bad as you're thinking, okay? So, guess what? This equals, now watch this, careful. Negative 1 over 8, x minus 1. You see the A is negative 1/8, see that? So B plus 9 over 4 times x minus 1 squared. C is a negative, so let's do a minus 1 over, you see what's going on here?
Yes.
And D is a positive, so plus 1 over 8, x plus 1. You do not have to expand. You can leave it just as it is right there. That's it?
You said you have to integrate.
Well, we're leading towards integration here, yes. But this is, remember, we're just splitting this up into partial fractions. Tomorrow probably we'll continue on, and then we'll integrate. But today is just splitting up into partial fractions, okay? I know, this lesson's long enough as it is, so that is your lesson on, now, the integrating part will come in part 2, but this is splitting up into partial fractions, and that's all we can do today. That's all I have time for today, okay?